Okay, today's class we're talking about energy and associated jargon. We're going to define some terms so that we can begin our unit on thermodynamics. The first word I'd like to define is energy, which is the capacity to do work. What's work? Work is the energy used to cause an object with mass to move. Heat is also the energy used to increase temperature. If we think of heat, what we should imagine is the agitation of molecules. So if molecules or atoms can be pictured as small spherical objects, when you increase their temperature they begin to jiggle around more frequently, or they take longer excursions in their movements. So for example, in a solid, the objects might be fixed in place, but they'll be moving back and forth within wherever they're located. In a liquid, they're sort of rolling around each other, but they stay fairly localized. And in a gas, the molecules are bouncing around, going long distances before they hit something else. But each time it represents a higher and higher level of energy, of agitation. Temperature then is a measure of the agitation of molecules. If your hand feels warm and it touches an object that's cold, you feel it as though it were cold. But what's happening on a molecular level is that the molecules in your hand are moving faster than the molecules in the object that you're touching. And by touching that object, you're transferring the momentum of your molecular motions to the molecular motion of the molecules in the object. So now what happens is some of that thermal agitation has been transferred to whatever object you're touching. And the object that you're touching will warm up because that surface will now have greater thermal agitation. We should also review the units used in relation to work and energy. Most of the units that we're going to be using in thermodynamics involve three base units: length, time, and mass. Length is measured in meters, time is measured in seconds, mass is measured in kilograms in the international system, the SI system, where they use the French Système International for naming it. So if you want to use SI units, these are your base units: meters, seconds, and kilograms. For example, velocity is defined as meters per second, so m over s. Acceleration will be defined in meters per second, and you get meters per second squared. Force, which is given by the formula F is equal to ma, mass times acceleration, is measured in units of kilograms times meters per second squared. And that unit itself, which is made up of three base units, is called the Newton. So that's the unit we use for force. Work is done whenever you take a force and apply it over a distance. So if I take this eraser or this marker and I push it a distance of 1 meter, I've applied a force to move it, and I've applied it over a distance. So I've done work. Force times distance is in units of newtons times meters. When you multiply newtons times meters, you get another unit called the joule. And we'll see later on how those units are made up of other base units that work nicely to form a pattern. Power is defined as the amount of work done in a certain amount of time. If you do the same amount of work in a shorter time, you're developing more power. And the units of power are in joules per second. Joules per second also has its own name. It's called the watt. We're familiar with the watt in rating for light bulbs, but you can also name, say, you could rate the power of a car in watts. 1 horsepower is equal to about 735 watts. So to just review the units as they go based on the base units, these are all derived units, meaning they're made up of a bunch of other small units. We have velocity, which is meters per second, acceleration, which is meters per second squared, the Newton, which is kilogram meters per second squared, the joule, which is kilogram meters squared per second squared, and we have power, which is kilogram meters squared per seconds cubed. So you see how there's a pattern there: meter per second squared, kilogram meters per second squared, kilogram meter squared second squared, kilogram meter squared seconds cubed. So the very gradual build-up of the base units. It's a great way to memorize it. It really compresses the information into an easily digestible unit. And just to throw around some formulas, Einstein had his famous formula E is equal to mc squared. You'll notice that the units of mass are kilograms, the units of the speed of light are meters per second. If you square the speed of light, it's meters squared per second squared. When you put it all together, kilogram, meter squared, second squared, gives you units of the joule. So this is maybe one way in which he saw that there might have been a relationship between energy and the mass of an object. In chemistry, work is an important concept since the energy released by chemical reactions is measured in joules. We also have one unit that's sort of a holdover from older times. It's called the calorie. And there's two ways of representing the calorie. There's a small c calorie and a big C calorie. The calorie we're familiar with, which is the dietary calorie, is equal to 1,000 of the small c calories. And that equals to 4,184 joules. So the conversion factor between small c calories and joules is 4.184. Big C calories in joules is 4,184. Originally, the calorie was defined by James Prescott Joule, who did an experiment with a paddle turning in water and a mass hanging from a pulley, and he measured the amount of energy that was involved in letting a mass fall 1 meter, and he measured how much it changed the temperature of the water. The result was that to change the temperature of 1,000 grams of water from 14.5 to 15.5 degrees Celsius required a unit of energy he called the calorie. Chemical reactions often release heat energy, and what I want you to come away from this lesson with is the notion that the energy that is contained within chemicals releases energy, but that energy comes out in the form of heat and in the ability to do work. And this is how we show that. That energy is a mixture of heat and the capacity to do work. The way you could maybe paraphrase this equation is the energy of a chemical reaction comes out as a mixture of heat and work. The whole thrust of the automotive industry and engine technology is to increase the amount of this, and perhaps maybe even decrease the amount of that. So if the fuel has a certain amount of energy, when you burn the fuel inside of a confined space, you can make the fuel do work. That's what the internal combustion engine does. And the more energy you get in the form of mechanical work, then the more efficient the engine can be said to be. We'll stop it there.